So let's start our second meeting. Hello everyone, this is Edison, and today we're just going to talk about the control systems and actuators and sensors. Those are basically the three main components of a robot, main control components. You also have your mechanical systems, but that is not something that we will be talking about too much. Just a fair warning, I'm about to drop a lot of concepts on you. We weren't able to find a room for today's meeting or today's recording, I shall say. This recording as well as the slides will be uploaded, and even if you have any questions afterwards, you can always just feel free to DM me or one of the execs. So let's start with a control system overview. Let's think about what makes up a robot, right? You have your mechanical components, which is basically just like your standard like aluminum beams, aluminum channels, and you have your screws, your shafts, all that like mechanical stuff. It's fairly structural. It's more like if you build a robot entirely out of mechanical components, it will be able to move, but it won't be able to move by itself. As in, you can make pivots, you can make joints on it. Like you can like move it if you like move it by hand, but also you won't be able to move it with a motor because motors are in the actuation and control system. And in the middle, we have control and actuation systems. This includes your sensors, includes your main your kind of like brain, so to speak. It's like a place where all your like code is run and all your sensors and motors connect to. You also have your motors, your so like your pressure cylinders, like stuff like hydraulics, pneumatics. Those are also part of the actuator system. And the term actuator is mainly just like describing anything that moves by converting like or like whenever it takes in a signal, it will move like a controlled movement. Is what I'm trying to say. And on the right side, you just have code. That code obviously controls your robot. Fairly standard stuff. So let's take a look at a standard VEX control system. So let's say I want this motor to move whenever I press the sensor, right? On the left side, we have the sensor. Not every robot has to have this. Most robots do have this because it is pretty useful. It's like if a robot doesn't have this, it's like having a person who's blind, deaf, and can't feel anything at the same time. Kind of useless, I'm not gonna lie. In the center, there is a control device. Like a lot of us call it the brain. Realistically, it's just something that runs the code, does the logic to make sure like everything works as intended. On the right side, you have your actuators, which is like whenever you finish processing the information from your sensors and everything, you need to output it into the real world by some means. The most common one is going to be motors that you see in competitions. Not even competitions. Motors are just generally in almost everything. But we will most likely also start working with pneumatics, which is gas cylinders that contract or expand a set amount, basically. So instead of like a motor input, which just like spins this direction, spins that direction, spins this at this speed, spins that at that speed, cylinders are more like binary. So it's either extended or contracted. Now, yeah, so this is the RoboMaster version of that. It's a lot more complex, but if you think about it, it is generally the same. On the left side, you have sensors. On the right side, you have actuators, and in the middle is everything in between. So a big difference between those, but is that there are a lot more communication going on between those. For example, if we were looking at the left side, the sensor might want data for what frequency it operates and how accurate, basically how fast and how accurate you want to be, right? The camera communicates through USB, so it's not your standard like UART or whatever cable. And of course, there is going to be data transferred from the PC to the USB. And you can see you have like three like control devices on this page. You have like two PCBs or like two brains, so to speak, and you also have a mini PC, which is like the main difference is like the PCBs or like the Roadmaster development boards. Those are normally called I think it's a Chinese notation, but it's normally a little bit like down. Like I don't know how you like explain it. It's like lower level is what I'm trying to say. And then your mini PC, of course, runs Linux, runs Windows. It's going to be higher level controlled. Sometimes you can just completely forego the lower level ones and just control everything with the mini PC, but we're probably not going to do that because that makes it a lot more complex. So with that overview done, let's move on to sensors themselves. So what are sensors is primarily something that you might be wondering right now. Sensors basically provide feedback to the brain. It is like a lot of sensors do resemble human senses. So like let's say for example your eyes, like sight. You can use a camera. Cameras are technically a sensor in this case. You can also say, okay, like when I touch something, I feel it. That is a touch sensor. And yeah, so your programming team can use this information, whatever information the sensor provides, and it will adjust like what the robot does in real time. And some sensors may require input. Let's say, for example, you want a camera. You have to tell the camera, okay, what frame rate to run at, and stuff like that. And the camera will like run at that frame rate and feedback information based on whatever input you give it. Nearly all sensors gives you output. I said nearly all because I wanted to be sure that I don't give out like false information, but so far all the sensors I've seen, they all give you output because that's the entire point of sensors. Sensors may use different communication protocols, which is something that we will touch on very shortly. It's like people speaking different languages. If you go to China and then you start speaking like Spanish, no one's gonna understand you. Yeah, so that's what it's like. So let's do a communication protocol speed run. This is just where the conceptual part starts, unfortunately. Don't worry about it if you can't memorize them or like understand like too much of them for that matter, because this is mainly under the control teams or like software teams umbrella, and they'll have to deal with it in much more detail. So let's start with GPIO. It's a digital input output. So GPIO stands for general purpose input output. You have two states, 1 or 0. If it's 1, it's giving out 3 volt 3 or 3.3 volts. If it's 0, it's giving out ground voltage. Input, like you have input mode or output mode as GPIO resembles. Input mode, they basically tell if like something is giving you a higher voltage or lower voltage. Output mode basically just gives out the higher voltage or lower voltage. Those pins are commonly used by like touch sensors, because obviously touch sensor you can just connect the sensor touch sensors are basically a button if you think about it, right? And you can connect one side of the button to 3 volt 3 and then the other side to input, and whenever you press it, 3 volt 3 connects, and then input gets pulled up and it reads 1. Also commonly used by LED lights in output mode. So if you connect the other side of the LED to ground and then you pull up or pull the pin to 3 volts that's connected to the LED, it will turn on basically. For encoders, encoders are basically two digital channel devices. It's a bit odd. We will probably touch on this in a control course specifically. Yeah. So let's move on to analog. Analog is still technically GPIO. It is still the same pins, but you configure them to instead of reading 3 volt 3 or 0 volts. You now read the voltage to determine a percentage of how high this voltage is in respect to 0 to 3.3. Input output still gives the same stuff, like a percentage, of course, and it is commonly used by potentiometers or accelerometers, stuff like that. Let's move on. So PWM is digital. It stands for pulse width modulation, and basically what we're doing here is we're outputting a square wave, right? Square wave, and then we're trying to tell how much the square, we can see on the bottom left here, we're trying to tell how much the high voltage is in respect to one period cycle. And by period or cycle, I mean from the top, the start of the high voltage to the next start of the high voltage. So we're trying to look at what percentage this part is in respect to this part. And this is very useful because a lot of servos, those small, there are small motors basically that go to one specific position once you give them a PWM. So those motors usually use a 5% to 10%, meaning they from the leftmost position it's 5% and rightmost position it's 10%, and so that's the way that we use to control it. So you can see it is commonly used by servos and motor controllers because PWM is really good with controlling actuators. You also have serial buses. This includes your I2C, UART, SPI, CAN bus. Lots of names, but the general concept is always, okay, we're going to read the ones and zeros from GPIO in series, and then we will be able to transfer some more information than just ones and zeros. There are a lot of different communication protocols, as I've said, and each of them have very different connection conventions. So if you look at UART, you'll notice that the the host device and the device that's receiving, it's your transmission port does not necessarily have to connect your transmit. It's your transmission port on one device connects to your receiving port on the other device, and it's flipped also, and you connect the grounds, right? You also have but you also go onto let's say SWD for RoboMaster, and then you realize, okay, now the pins are you have a clock pin and you have a DIO pin, and then that one you have to connect them to the names that are the same. So it's for each protocol, just make sure you read the documentation, or at least do a Google search to make sure that you're not connecting the wrong pins to the wrong place, or else it might take you a few hours of debugging to not find the issue. Those are commonly used by LiDARs, brains, anything that requires data that's not 1 and 0 or an analog data or PWM. It's okay, if I want to transmit something like a specific number, then most likely going to be something that's serial. So let's run down a few sensor types and what they're used for. So yeah, switches. They are a button. Most of them do either 2 or 3 pins, and you just connect it to ground, you connect it to a pin, and you press a button, and then the pin basically reacts based on what voltage it receives. This one should be fairly obvious of how it works. So we now have distance sensors. This includes your ultrasonic distance sensor. You have LiDARs, which is kind of like ultrasonic, but it works with light. And you also have triangulation, which is like IR sensors. I've never used one of those. Those are fairly rare. Probably won't be using those in any of our competitions, but might as well include it here. It has different methods. Function is about the same. They just have different drawbacks and advantages. Just attempts to find the distance by using their various methods from the sensor itself to the like the object right in front of it, right? So you can use different protocols like this. A lot of sensors use analog, but you can also use digital because VEX I've never seen this, but the VEX sensor, the VEX distance sensor, uses digital. They use 2 digital pins. I'm not too sure how that works. I'm assuming it's 2 PWMs, but I'm not gonna question it. You also have UART, which is interesting on distance sensor. I2C, very standard for a lot of sensors. And let's move on to potentiometers and encoders. So those two are like what we call rotary sensors, right? Encoder, like biggest difference between those two is potentiometers. They usually have a set detection range. So let's start from 0 degrees. Let's start from 0 degrees. We can measure up to like 270 degrees, but after that, it either doesn't measure or like some potentiometers have a hardware limit where if you go over that, that just breaks the potentiometer. But for encoders basically they can just keep on rotating forever. Yeah. They normally use two digital pins, and what they do is they have like a square wave that is offset for each channel. And so, like when you're spinning one direction, like the increase, like the pull up and pull down pattern is different from when you spin it the other direction. It's quite an interesting concept, but I'll probably include a video sometime in the future just explaining how that works, because like you really do need to visualize how it works in order to understand it. So the communication difference between those two is that potentiometer commonly uses analog, which means it is trying to send a voltage like from 0 to 3.3 volts back into a pin. But encoders use 2 digital signals, as I've said. So we have color and light sensors. Those are like, well, they basically you plug it in, you aim it at something at like a specific distance. It tells you what color it is or how bright it is. It is sometimes used in VEX. I haven't seen it used in RoboMaster yet. So like because obviously we've got cameras and normal light sensors don't really do anything. So it uses like GPIO analog or type of serial. Like it depends on how packaged the sensor is. Like a more packaged sensor will generally have like higher level peripherals. Like let's say if you have like some sort of serial, it's probably more packaged than like something that just gives you a few pins and you have to program everything yourself. So if we do end up using those sensors, just like then you like buy something with like the logic we're already done, so we don't really have to like do it like from the ground up. So we also have accelerometers and gyroscopes. Accelerometers basically tell you what acceleration you are on the 3 axes and the 3 rotation axes. And gyroscopes, they just tell you what rotation you're on. So those sensors, they generally need to be calibrated each time that you try to use it. So you let's say you turn out your robot. You have to ensure all hands are off your robot and it's stationary for like a few seconds after just so that everything gets calibrated, and then you can work on the robot again. VEX has a package sensor that has both accelerometers and gyroscopes, I believe. But RoboMaster, they're built into the motherboard, or like the control board. And if you want to use them, you do have to use it from the schematic. It's like generally because it's on the board, you have to start from scratch. It's a lot less packaged than a ready-made sensor. It's difficult to code. Logic might take a while to figure out, so good luck using it. And it uses analog or like serial communication. Depends on like which sensor it is. So with that many sensors, you might be asking yourself how you want to choose a sensor, right? So I've come up with 3 questions you should always ask yourself just to make sure you choose the right sensor. The first one being what it needs to do. Like obviously, if you want to find a distance, your primary choice is going to be like some sort of a distance sensor rather than a brightness sensor, for example. You want to know how accurate and precise it has to be, just so you if you already have a camera on the same axis of the distance that you want to measure, if it doesn't have to be too accurate, like if it doesn't have to be in like centimeter accurate, then you can probably use the camera to estimate the distance, right? But if you want it to be very accurate, then you'll most likely need a distance sensor. And you also need to know what input or output it needs, because obviously, like if you don't have the input it needs, you won't be able to use the sensor. Although like a lot of sensors don't require input, you should still like take note of that. Output, if you can't really use the output, then what's the point of putting that sensor there? You can't make use of it, then you might as well not have it there. So let's talk about an example. You need to find the range of a robot to a certain object. Let's call like that certain object like a field wall. You want it to act like a laser, which means that we want it to have a very small field of view, so it would only act in front of act for objects that are directly in front of it instead of like something that's like 5 centimeters above that position. You can provide like all serial communications, and then you can provide like a 5 volt and a ground connection, because most sensors do require either 5 volts, 3.3 volts, and a ground connection. So based on this, you can pick a LiDAR sensor. Your range basically limits your selections to distance sensor, right? You also want to react to the object directly in front, which eliminates like most ultrasonic sensors, because ultrasonics do tend to have a larger field of view, which in this case is not really good, because you want something that reacts very, very precisely. For ports, the sensor can work with either UART or I2C, which means we do have the peripherals to work with it. Keep in mind, UART and I2C both have transmission as well as receiving pins. So you don't have you can just group those two into one and just make sure you have that one peripheral, and you will be fine. So let's talk about the brain of the control system. So let's start with VexU. For VexU specifically, your brain is going to be the Vex V5 brain, and that is the only allowed brain for this competition. 21 smart ports is what they call those RJ something ports on their website. They also have 8 3-pin ports, which basically supply a voltage pin, a ground pin, and a signal pin. You also have micro USB for programming. A bit old of a port, but it works for a while. There's a battery port, and there's an SD card for some reason. And the screen is also a touch screen, and whenever you're running your own program, you can actually customize it to react to the touch screen and stuff, which is pretty rare nowadays. Pretty good. Too bad it's not a robot where you can't touch. So for RoboMaster, we're just given a PCB. They just put a few ports on it and then put a piece of rubber on top, so it looks like less of a PCB and more like a development platform. So realistically, this is just a circuit board with a chip on it. But availability depends on which board it is, right? You have more ports with the Type A board on the bottom, but generally we use the Type C board because it's gyro and accelerometer are technically better. You can technically design your own boards. I would suggest that you don't do that unless you're very dedicated and you hate yourself. And both of those they are programmed through SWD. It's called serial wire debugging. It's basically 4 pins that you plug into a port. Let's say this is the SWD pin. It's just one of those connectors that you just plug in, and then the other end they just break out 4 wires, and then you plug it into a debugger, and then you program through the debugger. So yeah, you do need a serial wire tool to work with it. SD-Link, SD-Link 32. You have J-Links. Those are basically just serial wire debuggers that you can buy on the market. I do have a few of those. Try not to buy them from Amazon. They're way too expensive. I've bought like 5 from China that seemingly work perfectly fine. So I have no idea why Amazon sells them for that expensive. All right, so for custom PCBs, it is technically it is going to be easier than you think, but it's still like a pretty annoying task. This is the ones on the right. That is the schematic and board design that I made during, I think, sometime in summer. Pretty fun experience, but I wouldn't suggest you jump into this until let's say you're in like 3rd or 4th year, because it is quite annoying. So the main thing that you gotta do here, for those of you are interested, is for the STM32 chip or microcontroller, you need to connect an oscillator, outside like external oscillator. You need to connect all its source and ground pins. You put on reset pins, and then your SWD pins so you can program it. And then for the other pins, you can just connect it to whatever device that you want, and it should function fine as long as you have it set up correctly in the code. As I've said, we don't really need this at the moment, but it's something to think about, because just in case there's no other way to solve a problem, you can't, this is the thing that you have to resort to. So let's move on to actuator. Now this is the part where it gets a little bit more fun. So let's define what actuators is. Actuators are devices that produce movement by conveying energy that's being fed into them. So let's say you have a motor, you're feeding in electrical energy, and it conveys it into kinetic energy by rotating. So we're likely to use only 2 types of actuators in both of our competitions. One is going to be motors. The other kind is going to be pneumatic cylinders, which is pneumatics, basically. All actuators have some sort of controller. Some of them may be baked into the actuator itself. Like some of the motors might be inside, like the motor controller might be inside the motor. But just know that you generally just need a controller for everything. So let's start with the V5 smart motors. Their motor controllers, I believe, are baked into the motors themselves. And they're technically more a lot more packaged than you might expect, because instead of just like a simple motor with a gearbox, those actually have a PCB inside that reads all the data that you might want from the brain, and then it feeds it back to the brain, right? So this is the only legal motor for VexU. If you're in Vex, this is the only motor that you're going to be able to use. And the wiring is basically you just plug a smart cable in, and you don't worry about that for the rest of your life. Input, you can tell it to spin at a velocity or a position. Both are fine. You can also give it a torque limit, and you might be able to give it some other commands. You might have to find this out using your IDE. For its output, the stuff that it gives back to the brain, first of all, it gives you a encoder reading, which denotes your motor movement. You can also it'll also tell you what its current and power is. It'll also tell you what torque it's giving, and tell you what temperature it's at. It's generally very packaged. It does tell you a lot of information if you ever need to use it. Half of this information we'll never use, but it's good to have. So let's move on to servos. This is the thing that I talked about while explaining PWM. So you have 3 pins to wire, as you can see here. One is ground, starting from left to right, all right? One is ground. The second one is the source pin, the voltage pin. This is normally, you have to see what voltage it takes in. This one works at 4.8 to 7.2 volts. Of course, the higher the voltage, the higher the torque. And so this the second one is just a voltage pin, depending on what the motor wants. The third one is the PWM pin. So it just takes in the square wave, and it takes in the high voltage percentage, and then it just rotates to that position that's mapped out. Input, you just give it a PWM for position, and output, it moves, of course. And most servos don't have any other outputs, but there are servos that do feed back their actual position, just so the brain can make use of it. Generally, there is a closed loop control built inside the servo, because what they do is they have a small motor and a potentiometer, and this is why most servos can't rotate past a certain degrees, because that'll break the potentiometer, right? So motor is connected to a bunch of gears, it goes up, and then potentiometer is directly connected to this output gear. And yeah, so most of them, they do closed loop control just to make sure like it's supposed to go to this position. But there are times where, like, let's say I just hold it there, like it's not able to go to that position no matter how hard it spins. Then if that shows the advantage of having a cable that feeds back to the brain, because the brain will be able to know that the servo is not at that position, and it will be able to make adjustments accordingly. So let's talk about brushless motors. In RoboMaster, we generally just use brushless motors because brush motors are a lot more annoying. Like, they heat up a little bit more. They're less efficient, and most importantly, they do break down over time a lot more because you have a brush that's going into the motor, so that will gradually wear down over time. So most brushless motors, they support either PWM or CAN. Most of them, from what I'm aware of, they just support CAN, but PWM is also pretty popular in motor control. For wiring, PWM technically only needs 2 wires, but most places do seem to use 3 wires for that. You have CAN bus, which is just 2 wires, and you also have to add on your power cables because you need to supply powers. And those PWM or CAN cables, they are generally very thin. You don't want to supply any meaningful current that will drive the motor through that. For input, you just give it a current. You just tell it to spin. Like it's just like you can only tell it to spin, like, to use this amount of current. What you can't do is tell it to spin at a velocity, which is a very different point from VexU, like the Vex motor that's very well packaged. Current in motors, they basically control your acceleration. So let's say we can't keep on giving it a set current, the motor will keep on accelerating. It's how it works. It will give you output of like motor movement. Encoder readings, of course, it just tells you how much this motor has been spinning. It will also feedback, sometimes it will feedback temperature, your current, some power, torque, basically all the things that VexU has. It's most of it will have on most motors. Depends on which motor it is. So one note that I will like to add on is that the PWM mode in this specific motor that I have shown on the right here, that actually does a closed loop control because PWM cannot send data back to the host. So what they do is they just do the closed loop control inside of the motor controller, and they just write PID there. And but the downside of that is for CAN bus. Like without CAN bus, you can't really send any data back. And for a RoboMaster, generally you want data for like pretty much everything that you can get. So a lot of teams do elect to use both communications. They use PWM for controlling the motor spins and CAN bus to receive the data. The chassis that I brought to the Clubs Day and the MSC Day events, those were controlled purely off of CAN. I just wrote the the PID myself. So yeah, generally, like, those are how brushless motors works. It might be a little bit more complicated, but the control team will deal with it. So let's move on to our conclusion. So you want to ask these questions whenever you're trying to choose hardware, right? You need to ask for its purpose, like what is useful, and you also need to ask yourself how you want to use it. Like this is going to be your method. Like let's say the distance sensing example. You need to ask yourself how you want to use the distance sensor, like which like kind of distance sensor will give you the best results, right? You either want something that will just give you the distance in like that general vicinity, like an ultrasonic sensor, or you want something like a lidar sensor that just like it's like a laser, just go pointing straight forward. Those two are very different in respect to their use cases, even though they might be the same sensor and give the same output. Uh, you also need to know what to feed it, because some sensors like lidar they might want I2C, while ultrasonics they're a lot more simple. They just want to plug into an analog and just start working. You also need to know what it gives us. So again, ultrasonic sensors they just give you an analog output and they usually don't require any input. But for lidar, they usually want you to give it like some kind of input for some reason. So those same questions also apply to anything that you want to use, like motors, servos, anything that you can think of. And yeah, anything like that's not included in the slides, like any sensors, any motors, feel free to use them as long as you ask yourself those questions. You can't go wrong. But except like if you're in VexU, then you're pretty much limited to VexU Vex motors. But I think you can use custom sensors. I'm not actually too sure about that. But yeah, go wild. Just research as many things that you like. Some like who knows? We might be just yank it and like use it on the robot. All right. So there is two things that we want you to do. So the first thing is just review the slides if you need it. Obviously, it's very conceptual. If you have if you have any questions, feel free to ask me. I'm very aware that I stuttered like 50 times during this presentation, so you might be very confused. So you can like the second task that we want you to do is like if you can just change your username on the server to your first name so we can identify you by like your name rather than your online name, because what I tend to do is if you have a name online or like on Discord and then I meet you in real life, I will start by addressing your online name instead of your real life name, because that is the kind of person I am. I blame ADHD. I'm sorry, but please do me a favor here. All right. That is pretty much everything. I'll see you in the next meeting. So for the next meeting, we'll probably start splitting up into your mechanical, your control team, and your software team. You also have and your CV team. A CV team, it's gonna be a lot more difficult. I'll just spam you with resources, but presentation is probably going to be very difficult to make. But for the other two teams, both in VexU and in RoboMaster, we will probably start splitting it up because from this point forward, everything is going to be a lot more different. And yeah, we'll see if we want to do more recordings or do in-person meetings, because in-person meetings might be a little bit easier for people to understand. But we will have to schedule for like very separately for other teams, because those are going to be very different presentations. Again, thanks for watching the video, and please do complete the to-do list, and I'll see you next meeting. Goodbye.